Hello, everyone. Good morning. I'm gonna go ahead and start as people keep coming in. Um, so today we're gonna be, so today's lecture 5, and we're gonna be talking about stereochemistry and continuing that topic. Okay, so this is just an overview of what we're gonna be talking about today. So we're gonna talk about stereochemistry of alkanes and a little bit also concerning rings and then stereochemistry of alkanes. Before we do that, I kind of wanted to do a little review from what you guys learned on Monday. So if you guys remember, you guys talked about isomers, and that isomers are molecules that have the same chemical formula, right? There's two different type of isomers. You have constitutional isomers as well as stereoisomers. So constitutional isomers were molecules that have the same chemical formula, but different connectivity. So for instance, you guys see these two molecules. The chemical formula for this is C3H7F1, right? So they have the same chemical formula, but the connectivity between where F is connected to is different, where that F is connected to this carbon in this one, but it's connected to this one, this carbon and this one. So these are constitutional isomers or structure isomers. You can say either or. And then you have stereoisomers, which have the same chemical formula as well. But so they also have the same connectivity, so same chemical formula, same connectivity, but they're connected differently in spatial arrangement. So for instance, this molecule right here, I'm going to try to zoom in so you guys can see it better. So that one right here, right? So this carbon right here has a bromine, a chlorine, a fluorine, a hydrogen attached, and also this one. So these two have the same connectivity, same chemical formula, but the way these are arranged spatially are different, right? So the example I just did is a type of stereoisomer. In this case, it's an enantiomer. So this molecules right here are enantiomers. Enantiomers again are mirror images that can't be superimposed. So these are mirror images and cannot be superimposed. And then you have diastereomers, which are also a type of stereoisomers. So diastereomers are non-mirror images and are also not superimposable. So for example, this one right here, these two molecules are not mirror images and you can't superimpose them on each other either. One that we did not talk about was the cis and trans isomers. So we're going to go more into depth on these type of diastereomers. So before we go into that, I just wanted to kind of test your chemistry intuition and see if someone can guesstimate if this is a cis or a trans. And feel free to be wrong. We haven't talked about this. But does anyone want to guess if this is a cis or a trans isomer? Feel free to send me a chat or just say it out loud.
Is this cis?
Yeah, so this is cis, and you can think of cis of being or meaning same side. So in this case, we're meaning same side in relation to the double bond. So we look at the double bond right here, this one right here. We're going to look at kind of try to divide this right between up and down. And we see that these two are both going up. So they're cis, they're going to the same side. And we'll go more into detail on this later on the next slide. So let's do that. So cis and trans is a more formal definition, right? So cis is when two identical groups. So emphasis on identical, we're looking at two same groups that are pointing in the same direction from the plane of the ring. So this is where the rings come from, or the double bond. Trans is two identical groups. And again, identical groups, we're looking at same groups pointing in the opposite direction from the plane of the ring or the double bond. So in this case, we're talking about rings and alkenes. And if you notice rings and alkenes, or if you guys remember from Gen Chem, these have restrictions in rotation. If you remember, these double bonds are, let me write it down, sp2. right? sp2 plus p. So the double bond itself is just an overlap of p orbitals. So let me erase that. Right, here's a picture, right? So the overlap of these p orbitals is what the double bond is, right? So if you try to rotate, for instance, this bond right here, and you only rotate one of the p orbitals, then there's going to be less overlap, and eventually you'll break the double bond. And you don't want that because that will be a different molecule. So there's restriction in rotation when it comes to double bonds, and as well as rings, right? Because if you try to rotate it, eventually you can't rotate it anymore. If you keep trying, you'll probably break the ring. So these two have restriction and rotation. So when we're talking about cis and trans, we're talking about the carbons that are in the double bond, or in the case of this ring, where these the same groups are attached to. So we're looking at two identical groups, in this case, chlorine and chlorine here. We're looking at these two carbons, right? So we try to first look at this one, right? These two chlorines are on the same side, that is cis. These two chlorines here are on opposite sides in relation to the double bond, so these are trans. In this case over here, does someone want to say, like, how do we know these are cis, right? Because it says right here that it's cis, but how do we know it's cis if we don't have a double bond? Just give it a try. You can also message me. So if you look at this one right here, what is different between these two? How can we tell which one's cis and which one's trans? Yeah. So the chlorines here are both wedges, right here. So both of them are wedges. Both of them are going towards us. So they're going to the same side. So this doesn't have a double bond. This is still a cis, right? And then this one is a wedge, one is a dash. They're going opposite directions. So this one is a trans. Okay. And then just to mention a little bit, we talked about nomenclature. You can also denotate that molecules are cis when you're naming molecules just by putting like cis hyphen and then the rest of the name, or trans hyphen and then the rest of the name right there. Does anyone have any questions so far? So there's two conditions when we're talking about cis and trans. So first, when we're talking about cis and trans, we're only looking at two carbons, right? Two carbons that are part of the double bond or which contain the wedges. If there's more than two that we're looking at, so for instance, these, we can't denotate this as cis or trans because we can't, like which one, like if we're trying to name this, which carbon are we actually looking at? We don't know, there's more than two, so we can't really note this as cis or trans. And then we're looking at, the two carbons, at least two of these carbons have to have the same substituent. So again, we're looking at two of the same groups when we're naming cis and trans. So the case right here, this one, these two double bonds, we're looking at the ones that are directly attached to either this carbon or this carbon. This has a bromine, this has a fluorine. Well, on this side, there's a chlorine and a methyl. So these two carbons don't have at least one substituent that is the same. So we can't also, we cannot denotate this cis or trans. Also, a thing to note is that if you have one side that has two of the same thing, so for instance, this two, we can't also like denotate the cis or trans because there's no difference between these two hydrogens, right? So like if we were to switch these two, we can't really tell whether it's cis or trans because it's the same thing in relation to the other side. Is there any questions on that? Did that make sense? I'm gonna take that as a yes. Okay, so also this is an example of when you can't name cis or trans because everything is the same, right? So it's the same, you can't say what's cis or trans, right? Okay. So let's do a little bit of practice together. Can someone tell me whether this molecule is number one, is cis, trans, or neither? Again, we're looking at what is attached to the carbons that are involved with the double bond. Right, somebody says trans, so that is correct. So we're looking at the same molecules, right? Or the same substituents, same groups. These are two methyls that we're looking at. So those are opposite sides, so they're trans. Let me write that down. Trans. So what about this molecule right here? Number 2. There you go. What do you guys think this is? Yeah, somebody said trans. This is also trans. So again, we're looking at the same group. In this case, we can do OH. One is a wedge, one is a dash. So they're opposite sides. So this is trans as well. Oh, that's an ugly T. Trans. What about this molecule right here? Number 3. Okay, so this is kind of tricky. So when it comes to rings, right, the carbons don't have to be side to side, right? And also a thing to note in this one, you have hydrogens that are not drawn. Sorry, that's a horrible hydrogen. Just know that's a hydrogen, right? So there's 2 hydrogens, and those are wedges, by the way. 2 hydrogens, both wedges going to the back. Do you guys still have the same answer? Yeah. So someone message says, yeah, so this molecule is cis, right? We're looking at the groups that are the same. In this case, both of the hydrogens are dashes. They're both going to the back. They're the same side. So this is considered a cis molecule. This one's kind of tricky, but just to mention that the carbons don't have to be next to each other, and sometimes you have to, remember that the hydrogens are sometimes not drawn there. So this one is cis. So what about number 4, right here? Is it cis, trans, or neither? Yeah, somebody said neither. This one's neither. And the reason why it's neither is because we're looking at things attached to these 2 carbons in the double bond. And at least, they have to have these 2 carbons, one thing or one group that's the same between them. In this case, all of them are different, so it's neither, right? So when it comes to molecules like this, right, we're able to use another system, which we'll talk about in a minute, right? So there's sometimes, such as an example, number 4 in the last time, where we can't use cis or trans, right? It doesn't work because they're different groups, but sometimes we still want to kind of note when there are different molecules, such, you notice this Br here, this F here, and notice how it switches in this molecule. Sometimes we want to be able to write the fact that these 2 are different in that aspect, right? So when we're not able to use the cis trans, but we still want to write that down, then we use the EZ system, and we'll learn about how to work that out right now. So this is a slide from from last summer. Buffon did this lecture, and I really like the slide, so it's here. So essentially, when it comes to the E and Z configurations and how to denote that, or how to know which was which, you have to first look at the higher priority groups, right? Higher priority is molecules that are higher in atomic number. So higher atomic number, higher priority. In this case, higher priority, when they're opposite from each other, we denote them with an E. If they're on the same side, we denote them with a Z. And an easy way to remember is Z as in same. You can just same. And if this is a little confusing, let me just make sure to draw it. So chlorine, and those are methyls, right? So chlorine is a higher atomic number than a carbon, right? So these are methyls. So then we'll realize that that's higher priority. And then this side, this is also higher priority. They're on opposite sides. So this is an E configuration. And then the same thing for this one. I know this is ugly drawing, but just know those are chlorines, those are hydrogens. Again, chlorine higher priority because it has a higher atomic number than hydrogen. They're on the same side, so it's Z configuration. So this is actually called the Kohn-Ingold and Prelog rules. So if you ever hear that, just know this is what we just did is that. A more formal way to explain this is that, let me give an example. So chlorine, I'm going to use the same example, right? So each carbon in the pi bond, again, we're talking about this double bond right here, and those carbons, right, are attached to two substituents. So in this case, chlorine and methyl. So for each carbon, you will rank the two substituents. So for this carbon, you rank this one and this one, and this one and this one, and denote it with a 1 or a 2, according to which atomic number is bigger. The atomic number would get a 1. So let's do that. So this chlorine right here is a higher atomic number than a carbon. So this is going to be 1, right? Same thing for this one. This is going to be 1. That's supposed to be 1. And this is a 2, and this is a 2, right? Whenever the ones are on the same side, right? Same side, this is going to be a Z. Whenever they're on opposite sides, it's going to be an E, which is what we did on the other slide, but this is just a more formal way of saying the same thing. So this is the same thing, right? So you're looking at higher atomic number is higher priority, right? Bromine is a higher atomic number than fluorine, so this is the number 1. This is the number 2. The same thing with this side. Chlorine is higher priority than H. Number 1, number 2. The number 1s are on the same side, so this is a Z. So this is just a quick example. So what happens when it's more complicated, right? Sometimes there's going to be a tie between molecules. So for instance, this molecule right here, right, we're looking at this double bond right here. So whenever you have two double bonds like this, usually they're going to tell you which one they want you to denote, whether it's E or Z or cis or trans. In this case, we're looking at this one right here. So let me highlight that one. First, right, you realize which carbons you're looking at. We were looking at these two carbons and then what is attached to those, right? First, let's look at this carbon right here. It's attached to a Br and a carbon, right? So we're looking at the things directly attached to it. So a Br and a carbon. We realize that the Br is a higher priority than C. So then this one's a number 1, right? But then when we go to the next one, right, to this carbon right here, we look at what's directly attached. It's 2 carbons, right? So both of them have the same atomic number. So you can't really say which one's higher priority because they're the same thing. So this is a tie. Whenever you come into that issue where you have to figure that out, right? What you do next is that you would look at what those 2 carbons are attached to, right? So we had looked at what was attached to that carbon, right? Next, we'll look at what is attached to these 2 carbons right here. So those 2 carbons right there, this one is attached to a carbon and then 2 hydrogens that are implied. So we will write that down, carbon, hydrogen, hydrogen. And then we will look at this one right here. What is attached to? It's attached to a carbon and then 2 implied hydrogens. So you would write carbon, hydrogen, hydrogen. And then it's the same issue, right? These 2 are exactly the same. There's no higher priority molecule as compared to the other. So we would have to keep on going, right? So we looked at these 2. Next would be looking at this one and this carbon right here and what that is attached to. So let's do that. So now we're looking at these 2 right here and what those are attached to. So this carbon right here is attached to an oxygen and then 2 implied hydrogens. So we write an O, H, H. And notice how we usually do the higher priority like molecules first, right here. We've been writing C first and HH, O first and HH. That usually helps when you start comparing them, right? So then let's look at this one right here. This is attached to a carbon, another carbon, and then an implied H. So we write CCH. And in this case, we can see that oxygen, right, is higher priority than carbon. So then we know we can denote this one right here a number 1. And then this one over here a number 2. And then we see that these number 1s are on the same side of the double bond. So this is going to be a C configuration. So this one right here is C configuration. And that's how you do it when it's a little bit more complicated. You kind of have to keep on going like throughout the branches. Does anyone have any questions for this practice problem right now? Okay. So I just want to note that some molecules can be named both with using cis, trans, and C and E isomers. So for instance, this molecule right here, right, we could look at these chlorines, right? This can be a trans, but also we can figure out that you can also name it an E configuration molecule. This one too. And again, remember, because we're looking at cis and trans, they're identical groups, so we can use cis and trans. And then when we're using E, we're using higher priority. So chlorine is higher priority, so it would be an E. And then for this one on the side over here, this one would be cis, right? And then you can also name it Z. But there's some molecules that you can only denote with Z and E, but not cis and trans. So in the case of this one, this is what we had talked about before. You can use cis and trans with this, but you can use Z and E for this one. So we could realize that this is higher priority rather than fluorine, and then chlorine is higher priority as compared to methyl, right? So this would be a Z configuration. Does that make sense? Any questions? Okay, cool. Let's move on to a practice question. So does anyone want to try out this molecule? Is this molecule Z or E or neither? What do you guys think? Feel free to chat me again. Feel free to say it out loud. So someone said Z. So let's work this out together. So again, we're looking at this bond right here, right? We're looking at what is attached to those chlorines in that double bond, right? So let's start with this site first, with this chlorine first, right? We're looking at things directly attached to the double bond. So in this case, we're looking at chlorine. And then we're looking at this carbon right here. We realize that chlorine is a higher priority, right? So let's name that or number that number 1, and then number that number 2, right? Because chlorine is higher priority than carbon. It has a higher atomic number. Then let's look at this side over here. We look at this carbon and this carbon. Again, both of them are carbon, so there's no difference. We have to look at what those two are attached to. So this carbon right here is attached to the CH. And then this carbon right here, right? So let me just explain where the CCH is coming from. This is the C that carbon is attached to. This is the C that carbon is attached to. So C, and then the implied H. And then this one right here is attached to one C, and then 2 H's are implied. So it's going to be CHH. And then we can compare them. These two are the same. But right here, you have a C here as compared to an H here. So then we number this one 1, and then this one 2, and then this one Z. And somebody had sent Z, so you guys are correct. Is there any questions on this example right here? Okay. If you guys ever have questions, also feel free to put it in the chat and I'll answer it. Okay, so this is just the answer, so you guys can look at that later. So we're going to do more practice questions. Does anyone want to try number 1? So in this case, we're looking at this double bond right here that's highlighted in gray. Do you guys think that's Z, E, or neither? And if you don't know and you need to explain, that's also fair. You can also put it in the chat. Okay, so I've seen some answers, so let's go over this together, and then I'll say the answer at the end. So let's look at this carbon first, right here. Let's look at what that one's attached to. So it's attached to a carbon and then a carbon. So there's a tie. We have to look at what those two are attached to. So let's look at what this one is attached to. This is attached to 3 implied H's, right? So that carbon is attached to 3 H's. And then this carbon right here is attached to a C, an H, and an H. And then, so it's this C and then 2 implied H's. And we're not including, so like when I say this is attached to this, like this carbon, this hydrogen. Maybe you guys have noticed that I don't include what it was attached to like before, because we already looked at this. We're looking at things going forward. So CHH, and then this one HHH, right? I'm not including this one. So then in this case, we notice that this one, right, compared to, so we're comparing these two. This has a C, while this has an H. So then this one right here is number 1, and this bottom right here is a number 2. So then we look at this side right here. We look at what these are attached to, and in this case, there's an implied H, right, versus a carbon right here. So then a carbon is higher priority than an H. So then we could put that number 1 there, and a number 2 here, and then this is a Z. Does anyone have any questions on that? So in this case, this is Z configuration. Are you guys good with that one? I'm gonna take that as a yes, and then go to the next one. So for number 2, does anyone want to try it out? Again, we're looking at this double bond right here is highlighted in gray. You can also try to guess. Let's see if you get it correctly. Also, don't worry about being wrong. You guys just learned this, and some of these are tricky, which is why I put them there. Yeah, somebody said neither. It is indeed neither. So if you look at, and this is kind of, you can just look at it and realize that it's neither. So it has 2 of the same groups, right? So if you try to, denote which was higher priority and just keep on going like we did this one right here, it's all going to be the same. There's no difference between the two. So these, you can't denote Z or E when the groups are the same and they're attached to the same carbon. So in this case, it's going to be neither. Is there any questions on this one? I'm just going to rephrase that. So if you compare the 2 groups, this one or this one, let me highlight it. This one or this one, there's no difference in atomic number. Neither has a higher priority over the other. You can denote a 1 or a 2 to either, so you can't really tell which one, whether it's Z or E, right? So it's going to be neither. Okay, cool. Some of you got that correctly, so good job. Let's go to this one, number 3. Again, I'm going to highlight the bond we're looking at. This is a double bond we're looking at. Yeah, so this one's E, so let's go over it together. So we're looking at these carbons, right? Let's look at, oh, that's okay. Let's look at this side first, this carbon first. We know we're looking at what's attached to that double carbon in the double bond. So we're looking at this one and the hydrogen. This is a number 1, this is a number 2. Then we're looking at this carbon right here, right? This is a CH3 and this is an O. An O has a higher priority, so this is a 1 and this is a 2. They're opposite side from the double bond, so this is E, right? They're opposite. Okay, I think this is starting to make sense to you guys, but let's do a little bit more practice. That's the answers for the other one. Okay. So let's look at number 1 first, and let me highlight which bond we're looking at. So we're looking at this bond. What do you guys think? Is Z, E, or neither? Right, somebody said neither, so it is neither, because they have, so the H's are implied. 2 of the same thing are attached to 1 hydrogen, to 1 carbon, sorry. So you can't really tell whether it's Z, E, or neither. So, sorry, Z or E, so it has to be neither. So this number 1 is neither. There you go. So now let's focus on number 2, right here. This is the bond we're looking at. What do you guys think this is? Someone said Z. Yep, you're correct. So let's go over this together. Again, we're looking at these 2 and what is attached to those 2, right? So in this case, let's look at this one first, the side first. we'll compare this one and this one. We realize that both of them are C, so we keep on going. So now we have to look at what those two are attached to. In this case, this bottom one is attached to 3 H's. This one is attached to a C, an H, and an H. So then this one's a number 1, this is a number 2. And then let's focus on this side over here. There's a implied H right there. So this, this we're comparing a carbon versus a hydrogen. We know a carbon has a higher priority, so it's this one, number 1, and then this is a number 2. So this is a Z isomer. So let me erase that because that's looking like a mess. And let me rewrite that, Z and N. Does anyone have any questions on what we have gone through so far? Okay, so let's keep on going. Let's look at this bond right here. Does anyone want to try out to see which one it is? Yeah, someone said E. It is indeed E. So let's go over this quickly. This is a number 1. This is a number 2, right? This is a number 1 and this is a number 2. They're opposite, so it's an E. Does anyone have any questions on the ranking or anything so far? Okay, let's go to number 4. We're looking at this bond right here. Does anyone want to try to guess? So some of you have tried to answer it, so let's actually go over this one. So it might be a little bit too tricky. So in this case, we're looking at this side over here, we have an H, and then we have a carbon. So we know that the carbon is number 1 versus hydrogen is going to be a priority number 2. We look at this one right here, and then look at what they're attached to. There's 2 hydrogens, right? So then it's the same thing. Sorry, not 2 hydrogens, 2 carbons, right? So they're the same priority. So then we keep on going. First, what is this one attached to, right? This one's attached to a carbon, a hydrogen, and a hydrogen, versus this one that is attached to a carbon, and a hydrogen. So let me show you where I got that from. So again, we notice that these 2 are carbons, so then we have to look at the next step on what are these attached to. So this is attached to carbon, hydrogens, right? And then this one is attached to 1 carbon here, 1 carbon here, and then a hydrogen that's implied. So then we notice that this one compared to this one has 2 C's. So this one's going to be, we're going to denote this side a number 1. This is a number 2. So then it's a Z. Does that make sense to everyone? Is there any questions so far? Okay, cool. So let's do this question right here, number 5. We're going to focus on this double bond right here. Does anyone want to try to answer that to see if it's Z, E, or neither? You can put it in the chat. You can say it out loud. Yeah, someone said E. It is indeed E. So let's do it real quick. There's an implied H right here. So there's a carbon and an H. So you know carbon goes first. It's first priority, has a higher atomic number, and then hydrogen gets the 2. And in this case, this might, sometimes it's just easy to look at it and see that this keeps on going. And if it keeps on going, it's attached to a carbon as compared to this one that just kind of ends because it has 3 hydrogens. So you kind of can just look at that and see that this is a number 1, this is a 2. So then this is an E because they're opposite, right? Is there any questions on that one? Let me erase this real quick. And continue to number 6. So we're looking at this one right here. Does anyone want to try it out? Yeah, a lot of you guys are saying E, so it is E. So you can, again, just kind of look at it and see that this kind of keeps on going, and this is just an H. So you can just, this is a 1, this is a 2, this is a 2. So it's an E. Let's try out the last one, which is number 7 right here. So we're looking at this bond right here. Yeah, a lot of you guys are saying neither. It's definitely neither. It's attached to 2 methyls right here. So you can't really say whether it's one or the other. So it is indeed neither. Okay, so these are all the practice questions. These are the answers. Does anyone have any questions so far? Oh yeah, okay, sorry. I did in fact, I just realized, I saw the message. I just realized that it was pointing to this one and I was talking about this one. Okay, so we answered this one. Feel free to try this by yourself. I just realized I was looking at the other bond, but hopefully that still made sense and I didn't confuse you guys. Is there any questions so far? So this slide is going to be on Canvas. It's just if there's more complicated cases, if you guys want to read more on this, Mastering Organic Chemistry usually has pretty good explanations. And some of the examples I included today come from there. Also, for Monday's lecture, there's actually a written explanation of like chiral, achiral, diastereomers, and all of that that was talked about on Monday. There's a written kind of study guide on Canvas in the discussion section. It's also on the Wix website if you guys want to look at that. But I am done for my part, so let me stop sharing so Jennifer can start.
All right, thanks so much, Ashley. Okay, so I'm going to talk more about the stereochemistry of alkanes. So just load. So not this slide actually. Okay, so before I do that, I am actually going to do a quick review of some of the terms that we keep talking about because that's going to be very important for my part of this lecture. A stereocenter, that's the atom at which the interchange between 2 groups gives a stereoisomer. So the examples we've seen are asymmetric carbons, and as we just saw in Ashley's part, the carbons involved in double bonds and E and Z isomers. So what this basically means is that if you swap 2 groups at a stereocenter, you will swap the stereochemistry. So if you were to swap 2 of the bonds on an E isomer, it would become a Z isomer. An enantiomer is, I'm going to stress this, is the relationship between 2 molecules. So when it can have a non-congruent mirror image. So an enantiomer is kind of like a twin. You can't be a twin on your own. Saying that someone is a twin implies a relationship with someone else. So it's similar for enantiomers. And also the same thing with diastereomers. That's going to be a relationship between 2 molecules. With stereoisomers, so it's not the same molecule, but they are not mirror images. One key difference between enantiomers and diastereomers that we're going to talk about later is that enantiomers differ in configuration at all their chiral centers. And diastereomers differ in configuration at some, but not all of the chiral centers. And also chirality and achirality, these are properties of molecules. So chirality basically means that it can exist as an enantiomer, meaning that it has no plane of symmetry. So like, for example, the hand example, your hand isn't the same from left and right, which is the reason why the mirror image of your hand looks different from the hand. And then achirals, that's a property of molecules, meaning that it doesn't have a plane of symmetry, meaning that it looks the same as its mirror image, so it can't have an enantiomer. And so because we talk about chirality and stereoisomers so much, it's easier to have a naming system to talk about them because the easiest way to describe something is to name it. So we're going to talk about how we're going to name stereoisomers. So it's going to be based on the absolute configuration of molecule, meaning the actual 3D arrangement of the molecule. And that basically means that even though we can move around and rotate molecules, for example, if we draw them using a wedge and a dash drawing, that's actually kind of relative because if you were to flip over the drawing, wedges would become dashes. But we use an absolute configuration of a molecule, meaning that no matter the way that you view the molecule and no matter the way it's presented to you, you should be able to come up with the exact same naming system. And so we could keep like our naming system consistent. And so I'm just going to go over the steps. The first thing you have to do is to identify your asymmetric carbon and the 4 different groups around it. And you're going to assign priorities to the 4 groups. And you're going to assign priorities using the exact same Kahn-Ingold prelog system that Ashley just went over. And so once you've assigned priorities, you're just going to name number your groups 1 through 4. 1 is going to be your highest priority group, and 4 is going to be your lowest priority group. And then from this point, we're going to view the molecule along the bond from the asymmetric carbon to the lowest priority group. So that means that it's going to be kind of like a Newman projection situation where you have your asymmetric carbon in front and your lowest priority group in the back, so you can't really see it. And then because we don't really care about the substituents, if any, on the lowest priority group, we're just going to care about the free substituents on the front. And looking at those free substituents on the front, we're going to see if their order is clockwise or counterclockwise. If it's clockwise, it's going to be what we call the R configuration. And if it's counterclockwise, it's going to be what we call the S configuration. Okay, any questions so far? I'll give you guys a second to copy on these rules. Okay, and because I went through that very quickly, I'm actually going to demonstrate what I was talking about. So essentially, you have your molecule, and no matter the way it's presented to you, whether like what direction it's drawn on your exam, you're going to try to view it from the perspective of looking from this stereocenter, this asymmetric carbon, and with the lowest priority group in the back. So that's going to be number 4. And because of that, you can't really see 4, you just see 1, 2, and 3. And you look at the order of these molecules, and if it's clockwise, like in this example, it's going to be R configuration. And if it's counterclockwise, for example, was 1, 2, and 3, that would be the S configuration. And so because of that, we can have one consistent way of naming stereocenters, no matter what direction you're looking at. We're just consistently going to name them from this perspective. So I'm going to give you an example. So we're going to look at 3-chloro-1-pentene. I know we haven't gone over how to name alkenes, so don't worry about that. But all we need to worry about is looking at this. This is going to be our asymmetric carbon over here. And we're going to try to name this. So we need to identify our 4 groups, and I've already done that for you. But essentially, because we're doing it based on the atomic number, if you ever have a hydrogen, that's always automatically going to be your lowest priority group. So you can very quickly start looking at the other ones. And so we're going to look at it from the carbon and with the hydrogen in the back. And this perspective is actually the easiest way that we can assign priorities, because hydrogen's already in the back. We don't need to reorder these structures or anything. We can just draw it kind of like how it is. It's chlorine on top, and then this CH2CH3 over here on the right, and then the CH2 double bond on the left. So now we do assign priorities based on atomic numbers. So I'm just going to walk through that very quickly. So for the first priority group, that's going to be very easy because you have carbon here, a carbon here, and a chlorine here. And obviously chlorine is going to be your highest priority because it has the highest atomic number. So this next bit is actually where it gets a little trickier. So you have a carbon here and a carbon here, and this one's connected to another carbon, and this one's also connected to another carbon. And so how do you assign priorities in this situation? So there's actually a rule, and this also applies with when you're sending E and C isomers, where if you have a double bond, you count the atom it's connected to twice. So what does that mean? I'm just going to show you using the same system Ashley was just using. So for this carbon here, it's double bonded to this one carbon. So we count that carbon twice. So we act as if it's connected to 2 carbons. So carbon, carbon, and it's also attached to 1 hydrogen. And this carbon here is attached to 1 carbon and then 2 hydrogens. And so the first point of difference between these two is that the first carbon is the same, but the first point of difference is this hydrogen and this carbon. So this alkene group is going to have higher priority than this alkyl group. And so that's seen in the numbering system. And so looking at these numbers, is this going to be clockwise or counterclockwise? That's right, it's counterclockwise. And so is that going to be R or S configuration? Yeah, that's right, it's S. And so the way we denote that is, why is this not working? Okay, so the way we denote that is that we would name it exactly the same way based on whatever IUPAC rules we have. We haven't gone over this, but it's similar enough to what we see in the past that you should be able to understand it. And so we would just put parentheses, S, and parentheses, and then a hyphen to note that this is S configuration. So obviously the enantiomer would be the R configuration, and we would put R in front. And so that's how you name different enantiomers. I'll give you guys more practice on naming. I'm just going to go through the rest of my material just for time's sake. So whenever you see a molecule with only one chiral center, they can only have an enantiomer. So like the only other stereoisomer would be an enantiomer, obviously, because if you were to inverse it, it would be its mirror image and its enantiomer. There's nothing else you can do. If you didn't inverse it, it would just be the exact same molecule. And so when you do the mirror image, you would inverse the naming system. So in this case, 1, 2, 3. This is clockwise, that'd be R, and its mirror image, 1, 2, 3. This is counterclockwise, so that would be S configuration. So if you do the mirror image, you won't even need to go through the steps again. You would automatically know that you would invert the stereo, I can't make words, the stereoisomer name. So it becomes more complicated when we go into much bigger isomers. And so this is the case, in this situation, it shows why the nomenclature is so important, because if you were to draw a really big molecule, and if we didn't draw it in a very nice way, like it wasn't very like clearly like the mirror image, it would be very difficult to just look at it and see, is it an enantiomer or a diastereomer? So this is where the nomenclature comes into place. Because as we defined before, enantiomers differ at all chiral centers, and diastereomers only differ at some of the chiral centers. And so what does that mean? So I'm just going to use this example. So this molecule has 2 chiral centers, but this method I'm going to talk about would also work for molecules with even more chiral centers. But essentially, because this molecule has 2 chiral centers, there are 4 possible stereoisomers. And you can just look at that. I've listed them out here. So the stereocenters are at the 2 and the 3 carbon. So your different possibilities are that both your 2 and 3 carbon are going to be S conformation, or they're both going to be R conformation, or you could have conformations where only one of them is S and one of them is R. That makes sense? And so we can actually look at the molecules to see if they're stereoisomers. So if you can imagine that this line down the center, that's going to be your mirror, you can see that this 2S, 3S configuration is the mirror image of the 2R, 3R configuration. And then the 2S, 3R configuration, its mirror image is the 2R, 3S configuration. And so we can see when we inverse both of the stereocenters, that's going to be an enantiomer. So from 2S, 3S to 2R, 3R, that's an enantiomer. From 2S, 3R to 2R, 3S, that's an enantiomer. And the relationship between this one and this one, these are diastereomers because they're not the same molecule, but they're not mirror images. And it's the same here for this 2R, 3R and this 2R, 3S. These are diastereomers. And also between this 2S and 3S and this 2R and 3R, there's only one chiral center that's different between the two. These are diastereomers, and also this relationship is the same this way. There's only one different diastereomer. And so that can be a little tricky. So I made this chart to go over the relationships between the two. So once again, only when you invert all the stereocenters is it going to be an enantiomer. In any other situation, it's going to be the diastereomers. And so when you see like a big molecule that has like many stereocenters, instead of trying to like manipulate it in your mind or 3D visualize it, you can just identify the stereochemistry of every single stereocenter. And if you see that for the other molecule, they're all different, you would know it's an enantiomer. And if they're all, only some of them are different, you would know it's a diastereomer. So that's a trick you can use on exams and your homework assignments. The 2 and 3, okay. So I just use that to denote the 2 different carbons in our molecule. So it's the same system you would use when you're naming molecules. So you had the parent chain and you would number your molecules so you can number the constituents. So in this case, 2 and 3 are the carbon that are numbered 2 and 3. And the trick is that if you were to look at a molecule and a different molecule, and you wouldn't be able to figure out if it's an enantiomer or a diastereomer because it's so big and it's very hard to visualize that difference, you could just identify every single stereocenter, and then you would find the configuration using the rules I covered at the beginning of lecture, or beginning of my part of lecture. And so, and then you would identify all the stereocenters and the stereochemistry of the second molecule, and then you can just compare the two. So with that every single stereocenter, you would inverse it. So all the S's would become R's, all the R's would become S's. You would know that's the enantiomer. And if only some of the stereocenters change their configuration, you would know that's a diastereomer. Is that clear? Okay, I'm just going to move on. So I'm going to go over some practice of how to identify stereocenters, because how to name stereocenters, because that's a very important tool in organic chemistry. So let's just look at this first molecule. So once again, this is the easy situation where hydrogen is in the back. So can anyone try to name this molecule, or just like identify if it's R or S? So the first thing to do would be to number these 3 substituents. So you have chlorine, you have oxygen and you have carbon. Those are the first atoms connected to that stereocenter, so that's what you're looking at first. And someone said, is it S? That's pretty close. So let's look at this again. So which one's going to be your highest priority? It's going to be a chlorine because that's the highest atomic number. If you guys want to pull up a periodic table for reference, because I know that some of you guys haven't looked at this material in a really long time, that's completely okay, but I'm just going to give this to you. It's chlorine, and it's oxygen, and then it's carbon. And because these are all different elements, we don't need to go on to the next layer. We can just look at this layer. So it's going to be chlorine, oxygen, carbon. It's going in this direction because hydrogen's in the back. It's getting into perspective we need it to be. So it's moving in this direction. Is this clockwise or counterclockwise? Yeah, it's clockwise, so it's going to be I configuration. Oh, I gave the answer for that one. Okay. Anyway, and so this is going to be a trickier situation actually, where hydrogen is in the front. So how do you solve a problem like this? So there are a few tricks. If you're good at spatial visualization, some people can just rotate this bond, like this molecule in their mind, and then solve it from there. But a lot of people are much less comfortable with spatial visualization. So there's a few tricks you can do. One thing you can do is that you can just solve it as it is, and then understand that it would be the opposite direction when you were looking at it from the front. And so you would just flip your answer. So I'm just going to run for, so let's just run for this together. So we have bromine, oxygen, carbon. I'm not very creative for coming up with examples. So can you guys identify the priorities here and then the direction? Yeah, it's going to be bromine, oxygen, carbon. Bromine, oxygen, carbon. So from this perspective, it's going in this direction. Is this clockwise or counterclockwise? Yeah, it's counterclockwise. And so if you were to just end it here, we would say that it is S configuration. But remember that we're actually supposed to be looking at it from the other side, where hydrogen is in the back. So it's actually going to, from the front perspective, it would actually be moving clockwise. So what configuration would that be? Yeah, that's right. It'd be I configuration. And there's another trick that you can do. So like, remember as I said, at the very beginning of my part of the lecture, why do we need it from the other side? Just because if we were to do it from this side, we would say it's S. So we need one consistent way to view all molecules, just to make sure that no matter the way that we presented the molecule, we would name it the same way. So we want to be able to, like, if we were to talk about this molecule in a lab, and then we were to write a paper about it, and someone else wanted to study it, we want to make sure that they're studying the exact same stereoisomer. And so we want to make sure that when we're naming it, we're always looking at it in one consistent way. So no matter, everyone in the world knows exactly what you're talking about. And so that's the reason why we standardize the way that we look at it. So we have to look at it from the carbon in the front, and the lowest priority group in the back. And so the tricky part is that when you were given molecules, they're not always drawn in a very nice way with the lowest priorities in the back. So when it's something in like a situation here with the lowest priorities in the front, we have to either manipulate it in our mind or use some kind of trick. So that to make sure that the way that we're always naming everything consistently. And so there's another trick that we can do. So like, remember, as I said at the very beginning, if you were to swap two of the substituents at a stereocenter, you would swap the configuration. And so one trick you can do is that you can actually swap this hydrogen with some group in the back. So in this case, the bromine, and draw it like this. Load, okay. And so looking at this molecule, you know it has the opposite configuration or the inverse configuration as our original molecule. So because hydrogen is in the back, it's much easier to determine the stereochemistry. And then whatever stereochemistry we have here, or an S, we know that the original molecule has the inverse. So if you're looking at this, it's bromine, oxygen, and then carbon, In this case, it is counterclockwise, so we would say that it is S, and then we know that the original molecule is R. So essentially it's the same procedure that we just went through, but like a little bit more methodical. And so even if you're very good at visualization or very like comfortable visualization, having a bunch of tricks also just a good way to check your work on an exam. Also, just as a tip, another way I like to check my work on an exam is that because you're allowed to bring your model kit on an exam, sometimes if you have time, I would just like very quickly build the molecule. And then because of that, it's actual 3D object, I can just rotate it in my hands so that the lowest priority group is in the back and then see the stereochemistry from there. So that's one trick you can do. But for now, we're just going to make sure that you guys are comfortable doing it on pen and paper. So R and S. So this original molecule, that's going to be R. And the inverse of it is going to be S. And so we use the inverse because it's inverse, we can draw it in an easier way to visualize it. So we would swap this H and this bromine. And so this inverse is an S configuration, so we know that the original is R configuration. Just because we know the properties of stereocenters is that if you would swap two groups, you would invert the stereochemistry. And using that trick, we can solve a bunch of very tricky problems. So here's another tricky problem. What if, keep referring the answers, your lowest priority group is actually in the plane of the board? So if you're good at visualization or you're comfortable with visualization, some people can just be like, oh, you need to view it from this perspective. And then so you would draw it like this. So this group would be on the right and this group would be on the left. And so some people can just do that straight away. But if you're less comfortable with visualizations or you just want a way to check your work, you can use a trick that I just used, where you would just swap this hydrogen with the group in the back. So you would look at a molecule like this. So what is the stereochemistry of this molecule? Once again, it's bromine, oxygen, carbon. Right, so this one is going to be S. So if this one is S, what is this one? And remember, this one has the inverse configuration. What is the configuration of the original molecule if this one was S? Right, the original one is R. So, answers. So right, the original molecule is R. And if you use the trick where you would use the inverse configuration, you would go to S, and then you just remember just go switch from S to R. So yeah, this can be very tricky if you're doing it for the first time. So I would definitely recommend practicing this, especially on our homework assignments and our exams, so that you wouldn't mess it up on the actual exam. And so we're just going to look at one more problem, looking at this molecule. So our stereocenter, can anyone identify, first of all, which one's the stereocenter? Because this is a slightly bigger molecule. If this is 1, 2, 3, 4, 5, 6, 7, which number carbon is going to be your stereocenter? So 1, 2, 3, 4, 5, 6, 7. Yeah, it would be 4 because there's a hydrogen implied here. So this is the only carbon where there's 4 different substituents. And so let's assign priorities. So off the bat, from this carbon, you would look out and it's connected to 3 identical elements. So it's carbon, carbon, carbon. So you would actually have to go on to the next layer of connections in order to assign priorities. So this isn't as a clear-cut an example as I just gave before, but you would use the same process. So looking at this carbon, what is it connected to? It's connected to 3 hydrogens. And this carbon, what would we say that it's connected to? Remember that it's double bonded to this carbon. So what would we say the connections are? Exactly, carbon, carbon, hydrogen. And so this carbon, what are its connections? Yeah, carbon, hydrogen, hydrogen. So off the bat, we see that these carbons here, this carbon is bonded to 2 carbons, this carbon is bonded to 1 carbon, and this carbon is bonded to no carbons. And so because of that, we can assign priorities because the only other things they're connected to are hydrogens. So this would be our highest priority group, and this would be our lowest priority group. And because we've drawn this with hydrogen in the back, this is a very easy perspective. So what direction would we say this is going? Right, it's I, because it's clockwise. And then just to reveal the answer. Okay, and I believe that's all the examples that I came up with. And okay, it's exactly 12 o'clock. So thank you guys so much for coming today. If you guys have any questions, feel free to stay behind. But if you don't, you can go ahead and leave. Thank you guys so much for coming today.
Thank you.
Bye.